Hello everyone, my name is Dario Tarquini and I work as an intern at Exemplary Energy. In today's presentation, we'll be looking at our work on quality assurance of available meteorological data, where we investigated and compared different sources of meteorological data in order to provide quality assurance for their inclusion into weather and climate datasets, which is extremely important for applications to engineering and architectural modeling. We will start the presentation by looking at our detailed analysis of a set of reference meteorological year developed by the CSIRO, where after we identified substantial errors related to timing offsets, we tried to come up with a way to correct these timing errors, and so we proposed a workaround in the context of building energy simulations. We'll then move into comparison of available data from the Bureau of Meteorology and SOLCAS that we carried out in view of our other work, which will also be presented later today at the APSRC regarding the enhancement of our climate and weather datasets. And finally, we will touch on some further developments related to this work of quality assurance that we're carrying out. So, starting with a bit of background on this data that we analyzed, the CSIRO developed a set of RMYs, reference meteorological years, which was set as the baseline for the organization's work in creating projected weather files that are used to investigate the impact of climate change on building energy consumption and peak loads. These RMY data were generated by the New Zealand National Institute of Water and Atmospheric Research, NIWA, in the Australian Climate Data Bank format, the ACDB format, and they were then transposed into the EPW format, which is the Energy Plus Weather format. The ACDB format was created as the basis for climate information in the nationwide house energy rating schemes for the software that they were using, providing data for 70 geographic climate zones across Australia. And as of August 2021, the CSIRO has made these climate datasets freely available and have since been established as the de facto norm for building energy modelers looking to demonstrate compliance with the National Construction Code's requirements for energy efficiency, but also for a number of other applications, particularly in the renewable energy industry. And so, considering that the quality of these RMY datasets has a big impact on the energy efficiency of Australia's future building stock, we reviewed these climate datasets before the NCC 22 was published. Now, there are some key challenges when transcribing a dataset from ACDB to EPW format. When doing so, it is imperative to take into consideration the differences between different time conventions that apply to solar radiation data. For example, in the ACDB format, solar data represents the integral of solar irradiance over the hour centered on the timestamp. That is, each hourly data point represents 30 minutes either side of the timestamp. Whereas in the EPW format, the irradiance is reported for time intervals leading up to the timestamp. That means that it is timestamped at the end of each hourly period. And so now when comparing CSIRO RMYs to our dataset and considering that the time convention difference between EPWs and ACDB that I just described, we suspect that the CSIRO EPW has simply taken the ACDB data without adjusting for the 30-minute time offset deriving from different time conventions. And so failing to adjust to these can affect the overall heating and cooling consumptions resulting from building energy simulations, as well as time of peak loading. So utilizing our full 28-year historical weather record, we produced what we called a selected meteorological year, or SMY dataset, with months selected to replicate the CSIRO RMY, that is from 1990 to 2015, in the EPW format by concatenating the same calendar months for Brisbane, Canberra, and Melbourne. These allowed us to directly compare the data, as well as simulating with Energy Plus our archetypical 10-story office building, which complies with the proposed energy efficiency requirements of the NCC, to estimate the cooling and heating energy demand utilizing the CSIRO-RMY and the Exemplary SMY. As it can be seen from this graph showing the comparison of the diffuse horizontal irradiation in the Canberra climate, despite a few inconsistencies in the underlying data, it appears that CSIRO EPW approximately matches our data, but with a 30-minute time offset compared to our EPW. In fact, when comparing the CSIRO EPW with our ACDP, it can be appreciated how they seem to follow the same time convention. Thus, this is justifying our suspects on the errors introduced when transcribing the data from ACDP to EPW. Additionally, while transcription from ACDP to EPWs of instantaneous weather elements such as dry bulb temperature, dew point, atmospheric pressure, and wind speeds should be straightforward, it appears that the CSIRO method also introduces a 60 minutes offset error in these weather elements. And so, as I mentioned before, to understand how these errors are affecting building simulations, we utilized our 10-story office building to simulate CSIRO-RMYs and Exemplary's SMYs in the Brisbane, Canberra, and Melbourne climates to evaluate the building consumption, mostly heating and cooling. Here are the results from the simulations in Canberra. And as it can be seen from the chart, the effect introduced by these errors is obvious. Utilizing CSIRO EPWs, the monthly cooling requirements were lower and the monthly heating requirements were higher compared to the SMYs. This can be intuitive if you think that the 60-minute timing offset error moves the hot part of the day to 1 hour later relative to the building operational times. And so to overcome these timing errors, we rerun the simulations, but this time we modified the operational times. That means that we shift the operational times of our archetypical 10-story office building by 1 hour. And the results from these simulations, together with the ones we previously carried out, allowed us to isolate the impact of this error and estimate the effectiveness of the workaround. As expected, the tweaked operational times resulted in an increase in cooling requirements while heating demand decreased, so coming closer to the results using the corrected timestamp data. The charts on the left in this slide are basically the one we were looking at before, but with heating and cooling separated. On the right, the exemplary bars are the same. That means that they are the results coming from the simulations with the standard times, as in the charts on the left. What is changing is that on the right, the CSIRO result for both heating and cooling are coming from the simulation with the tweaked operational times. So these results show how this workaround is an effective strategy to correct the timestamp errors throughout the CSIRO climate files. The effect on the cooling consumptions is less noticeable, and so to appreciate it better, we wanted to show the percentage errors between CSIRO and Exemplary. And as you can see, it decreases when simulating CSIRO RMIs with tweaked operational times. On the other hand, when looking back at the heating consumption, it is easier to appreciate the effect of this workaround as the error drops significantly. Now, while the percentage error is overall below 10%, ideally it should be negligible after the workaround is applied. But the main source of discrepancy is still the 30 minutes time offset in the CSIRO solar data that we discussed before, which is still affecting the building simulations. And so to assure the quality of our analysis, considering that even after the workaround, there are still some discrepancies in the result, we also ran simulations with a third weather files, which was using CSIRO RMIs as a base, but with the solar radiation components substituted with the ones from Exemplary's SMY. And as expected, in the results from this simulation, utilizing standard operational times, the effect of the 60-minute offset errors of the other weather elements was still affecting the simulations. That means that although with lower percentage errors compared to the CSIRO RMYs, the monthly cooling requirements were lower, and the monthly heating requirements were higher compared to the SMYs. However, when simulating these weather files with tweaked operational times, the results were almost identical to the Exemplary SMYs, which is confirming that the discrepancy in the results is caused by the 30 minutes time offset in the CSIRO solar data. Now, moving on to the QA of some of the available solar data, Following the improvements to our real-time air weather data services that will also be presented later today, we performed quality assurance of solar data comparing the Bureau of Meteorology and Solcast data. Considering that as of May 2022, the solar data for our weather and climate tools has been courtesy of Solcast. The ultimate goal is to determine how the differences in these datasets could possibly reflect on building energy simulations. And as the BOM's ground-based measurements were available to us in alpha-hourly format, what we did was extracting data with the same time granularity from Solcast's global solar database, and we used the half-hourly GHI, DNI, and DIF that we previously produced from the hourly integrated BOM's gridded satellite estimate data. And here in these slides, we are presenting the results from Melbourne Airport in 2017 and 2018. Interestingly, while the percentage difference between BOM and Solcast satellite estimate data is very low, shown on the left, with overall values less than 5%, when comparing both Solcast and BOM satellite estimate data to the BOM ground-based observations, which we use as a base for our quality assurance, it appears that the quality of Solcast is higher. So now to conclude, we've been working with the CSIRO team over recent months to better understand the nature of the errors described in this presentation and to support the development of a permanent solution. And our expectation is that they will publish a solution in the future, but they have given no indication of when this will be available. Regarding the QA of available solar data, to understand how the differences that we show today can affect building energy consumptions and solar PV system simulations, we are aiming to create different RTYs utilizing the various sources of solar radiation and simulating a number of building archetypes with Energy Plus to estimate the building heating and cooling consumption, as well as performing solar PV simulations with System Advisor model to investigate into how the system output varies utilizing each dataset. Now, thank you so much for your time. Unfortunately, I believe we won't be able to have a QA session today. So if you have any question, please feel free to reach us via email. Thank you.